So till now we have discussed how we can use Nyquist stability criteria to tell whether a system is stable or unstable, right? And now we are going to discuss about relative stability. So we have already once heard about relative stability. What is it? It is the degree of the stability. That means if two systems are stable, then which one is more stable, which one is less stable? That is what we discuss in relative stability. So how do we find out the relative stability using Nyquist criteria? In order to study the relative stability, we will be making use of two new parameters. One is gain margin and the second parameter is phase margin. So what do these two parameters mean? Now before we discuss that, you need to understand that we are only considering the minimum phase systems here. Minimum phase systems only. For minimum phase systems only. First we will discuss the gain margin. You can write down the definition first. It is the factor by which open loop gain can be increased for the closed loop system or the feedback system to reach the verge of instability. Okay. Now sometimes the gain will be expressed in something called as dB. Okay, so we will discuss what is that, but first write down the definition. If gain is expressed in terms of dB, then the gain margin is the amount of gain that can be added for the closed loop system to reach the verge of instability. So in order to understand, let us take an example. Okay, so let us say this is the polar plot. The point -1, 0 is here. So the system is stable. Okay, now let us say the gain here is x. Okay, the magnitude is x. Now if you multiply x with the factor 1 by x, then what it will become? It will become unity, right? Now let us say the gain is actually being increased by this factor, then it will intersect the negative real axis at -1, 0. Okay, so then this 1 by x here is called the gain margin. It is the factor by which the gain can be increased so that the system will reach the verge of instability. Okay. Now what about in the case of dB? The gain in dB is written as 20 log mod g of j omega into h of j omega. Okay. So the magnitude here, we are taking the log of the magnitude and then multiplying by 20. Okay. So this is for the ease of mathematical analysis. Okay. Now what will happen at the verge of instability? At verge of instability, the magnitude g of j omega and h of j omega will be equal to 1. In terms of dB, it will be 0. Okay, because log 1 will become 0. Now what will be the gain margin when we are discussing in terms of dB? This is going to be the difference between this gain and this gain. Okay, so why we are taking the difference when it comes to gain in dB? Why we have taken the factor? So this will be clear. Factor is clear. X into 1 by x if you do, then it will become 1. So by this factor, if the gain is increasing, then the system will reach the verge of instability. In the log function, what happens is, since it is a log function, this division, we are dividing basically by x, right? That division will become difference, right? Log x by y is log x minus log y. So here the gain margin is going to be equal to 0 minus 20 log x. Okay. So now minus 20 log x, if you add to 20 log x, it will become 0 dB. So that means this amount can be added to the system before it becomes unstable. Here one factor that is important is the phase crossover frequency. So what is this phase crossover frequency? It is the frequency at which the open loop transfer function intersects the negative real axis. This is called as the phase crossover frequency and it is denoted by omega p. Okay. So that means g of j omega p into h of j omega p is equal to 180 degrees. So this point of intersection that we have seen here, this is where the frequency is equal to the phase crossover frequency, and this point is called as the phase crossover. So now we can write the expression for gain margin in terms of the phase crossover frequency. The magnitude x is equal to g of j omega p into h of j omega p. That means the magnitude at phase crossover frequency is equal to x. So what will be the gain margin? This will be equal to minus 20 log g of j omega p into h of j omega p, or you can write as 20 log 1 by g of j omega p into h of j omega p, because this minus here will become the power of whatever is inside the log function. Okay. So this to the power minus 1 will be 1 by that function. Now usually when we talk about gain margin, we refer to this form only. Okay. So that means when gain is expressed in dB, that is what we are talking about. Now how the different values of the gain margin will help us decide about the stability of a system. The first case is when the plot does not intersect negative real axis. Okay, so it is not intersecting at any point on the negative real axis. So this means what? The only intersection point will be at the origin. So g of j omega p, that is the magnitude at phase crossover. This is going to be how much? Simply 0, because intersection is only at origin. Okay. So then what will happen to the gain margin? This is equal to what? Minus 20 log the magnitude at the frequency, phase crossover frequency. Okay. Now we cannot substitute 0 at the magnitude, but it will be some positive value. Magnitude will be positive, which is very close to 0. Okay. And that will give you approximately infinity. Okay. So if the gain margin is infinite, it means that what it means? The system cannot lose stability even if the gain is increased by an infinite amount. Okay. So you can write here, therefore system gain can be increased infinitely without losing stability. Okay. So this is the first case. Now the second case is if the intersection is in between 0, 0 and minus 1, 0. Intersection is between 0, 0 and minus 1, 0. So what does this say about the magnitude? The magnitude will be less than 1, right? Mod g of j omega p into h of j omega p will be in the range of 0 to 1. So this means that the gain margin, which is equal to minus 20 log magnitude at omega p, will be greater than 0. So why it is greater than 0 is log of a number which is less than 1 will give you a negative value. But we have another negative value here. So overall it will come out to be a positive value. Okay. So if gain margin is positive, then it means that the intersection is in between 0, 0 and minus 1, 0, and this means that the system is stable. Therefore, system is stable. What about the case when the intersection is right at minus 1, 0? Intersection at minus 1, 0. That means that the magnitude at the phase crossover is exactly equal to 1. So what will happen to the gain margin? Minus 20 log 1. Log 1 is 0, right? So the gain margin is 0. That means that the system is at the verge of instability, right? Gain margin is 0 means you cannot add any more gain to the existing gain for the system to become unstable. Okay, even a little bit increase will result in the instability of the system. Therefore, system is on the verge of instability. And finally, the last case is when the intersection is beyond the critical point minus 1, 0. This means what? The magnitude at the phase crossover frequency is going to be greater than 1, and so this will result in a negative gain margin. You can thus conclude that the system is unstable. So what is the conclusion here? If the gain margin is greater than 0, then the system is stable. If gain margin is equal to 0, then you can say it is on the verge of instability or marginal stability. And if GM is less than 0, it means the system is unstable. Even from the definition of the gain margin, this will become apparent. Gain margin is greater than 0 means still some amount of gain can be added before the system becomes unstable, right? GM is 0 means no amount of gain should be added. It is just at the verge of instability. If gain margin is less than 0, then already the limit has been exceeded, so system is unstable. Okay, so it is pretty clear from the definition itself. So this is the final conclusion. Now how do you decide the relative stability using the gain margin? Okay, so greater the gain margin, greater is the stability. Okay, because greater the gain margin means that it is much farther away from the critical point. Okay, for example, you can take a couple of systems. Let us say this is minus 1, 0. This is one system and this is one system. Let us take this to be system 1 and this to be system 2. Then which one is more stable? The system 2 will be more stable because it is further away from minus 1, 0 as compared to system 1. Okay. So therefore, here in this case, system 2 is more stable. Both are stable, right? So we are talking about the relative stability here. Next we will discuss the phase margin. So we have already the gain margin. Why do we need additionally phase margin? We have already seen how the relative stability can be decided based on the gain margin, right? So how was it? Let us take this to be system 1. This is system 2, let us say. Then system 2 is more stable, right? It will have a larger gain margin. Okay, but sometimes what happens is the gain margin may be same, but still the relative stability will be different. So let us take an example for this. Here we have minus 1, 0, and one system we can take like this. Another system, I will use a different color. Let us say it is like this, but then it is coming like this. Okay, so here we will take this to be system 1 and this to be system 2. We can see that the system 2 is less stable than system 1. This is because it is much closer to the critical point. The parameter that is coming into the picture here is the phase. Okay. So for example, if you increase the phase of system 1 as well as system 2 by certain amount, then system 2 will become closer to -1, 0. Whereas system 1, if by same amount you increase the phase, then it will still be farther away from -1, 0. So that is why we say that system 2 is less stable. Okay. So you can write this down. This is less stable and this is more stable. So from here we understand that phase will also have a role to play in the stability, and that is where phase margin will be used. So you can write the definition of phase margin. It is the angle, usually in degrees, by which the open loop plot can be rotated about the origin for the system to be at the verge of instability. You can understand the phase margin when you consider the unit circle. So that means this point here is -1, 0, this point here is 1, 0. You can write down here, this is the unit circle. Okay. Now what you do is you draw a line between from the origin to the intersection of both the systems with the unit circle. Okay. So what are you going to see here? The system 2 can be rotated by this amount of angle before it reaches -1, 0. Remember that here we have taken the unit circle. Okay. So without changing the magnitude, if you are only changing the phase, then this is the angle that is required for system 2 to cross the negative real axis at -1, 0. Whereas the system 2 should be rotated by a greater amount of angle, okay, in order to reach -1, 0. So that means this is the phase margin of system 2. So we will write as PM2, and this is the phase margin of PM1 of system 1. Because a lesser amount of phase addition is enough to drive the system 2 to the verge of instability, the system 2 is less stable. Now how to find a mathematical expression for the phase margin? First we define a term called as the gain crossover. So what is this gain crossover? The point at which the magnitude becomes unity. Okay, and the corresponding frequency is called as the gain crossover frequency, and we represent it as omega g. Okay. Now what do we want is the phase at the gain crossover frequency. So if you take a system, we will take another system. Let us say the plot is something like this. Okay. And the unit circle you can take like this. So where will be the point -1, 0? It will be here. Now what is the angle that we want? This is the angle that we want. Okay. So how can we get this? If you take this will be the phase of the open loop transfer function, right? Angle GH. So what will be the phase margin? This will be equal to angle GH minus 180. Okay. So then you will get the phase margin. But there is one slight confusion that I want to clear here. If you are taking angle in this sense, this is the counterclockwise, usually we take the phase. Okay. Now another way in which you can write is this angle is also something that you can take, right? But when you go in this direction, you have to take the negative sign because this is clockwise direction. Now what will be the expression for phase margin in that case? It is going to be the phase that can be added to the existing phase to get minus 180 now, because you're going in this direction, right? So phase margin will be equal to the phase of GH minus of minus 180 degrees. So this will give you angle GH plus 180 degrees. Now this is valid. See, both the formulas are different, so there might be a confusion. So you have to write down here, this is valid for angle GH is negative, but by magnitude it is less than 180. We are talking about minimum phase systems only here. So it will be negative and the magnitude will be less than 180 only. When will this be valid? This expression is going to be valid when GH is measured in the counterclockwise sense. When GH is measured in counterclockwise sense. Here when GH is measured in clockwise sense. So you have to not to forget to take the negative sign. Now which formula will we be using? We will be using this formula. Okay, so why is that? The frequency here is omega is equal to omega g, the gain crossover frequency, right? So that means this GH here, this is at omega g, gain crossover, right? This point is important. Or you can write here once again, phase margin is equal to the phase of G of j omega g into H of j omega g plus 180 degrees. So usually we will get the phase by substituting omega is equal to omega g. And when you do that, you are generally going to get a negative value. Okay, when you do problems, it will become more clear to you. So that is why you will be using this formula only. Alright. So you have to ensure that if you are substituting the gain crossover frequency, whether you are really getting a negative value which is less than 180, then this formula will be valid. If not, it means that it is not a minimum phase system. Okay. So as long as it is a minimum phase system, you don't have to worry. You can just directly use this formula. So how will the phase margin value be for different stability conditions? If it is a stable system, then it means that the phase margin will be positive, right? Pm will be greater than 0. Even if you take the plot example, this is going to be unit circle. When will Pm be greater than 0? When it is intersecting the unit circle in the third quadrant. Okay, so that is when Pm you will get a positive value. So in that case the system is stable. Then what about on the verge of instability? So we know that a system is on the verge of instability if it is intersecting the negative real axis at minus 1, 0. So that means if you take the unit circle, this will be minus 1, 0. What about the plot? It will intersect right at this point. Okay. Then what will be the phase margin? The phase margin will simply be 0, right? Pm is equal to 0 because the line that we want is from the origin to the intersection with the unit circle, and this is coinciding with the axis. So phase margin will be 0. Okay. Then what about the case of unstable system? So the unstable system is going to have the intersection beyond minus 1, 0. This is minus 1, 0 and the plot will be intersecting in which quadrant? In the second quadrant. Okay. So now what will be this? This will be the phase margin, but now it will be in the opposite direction. So you will get the phase margin to be less than 0. Okay. So that means the phase margin is positive, the system is stable. If it is 0, then it is on the verge of instability. If phase margin is less than 0, it means it is the unstable system. What about the case of relative stability? That means if you take two systems which we know both of them are stable. So that means, let us say this is one system and this is one system. Okay. So then what will be the phase margin if this is system 1 and this is system 2? Then which system will have a higher phase margin? You can draw the lines here and you can compare. So clearly you can see that system 2 phase margin is lesser. Phase margin of system 2 is less than phase margin of system 1. So system 2 is more stable. This is how you decide the more the phase margin, more will be the stability. Okay, so this is how you decide the relative stability. Now both the gain margin and phase margin, we will use both of them. So the case when gain margin is greater than 0 as well as the phase margin is greater than 0, then there is no doubt the system is going to be stable. Okay, both are positive. What about the case when both are negative? This means that the system is on the verge of instability. Okay. Now if either one of them is negative or both of them are negative, then the system will be unstable. Okay. So if either one or both of gain margin and phase margin are less than 0, then the system is unstable. Okay.